So now we've established how to calculate the kinetic energy for a rigid body. And we've said that for the kinetic energy, there's a translational kinetic energy and a rotational kinetic energy. So now let's relate those to the work of a rigid body. We'll start with our definition that we've established for a single particle. And this is that the work done on any particle P that has mass that's defined by the position vector with respect to an inertially fixed point O along the path gamma sub P, then we've defined that as the path integral of the force P dotted with the differential position vector. We can also write this in terms of the power, which is the force dotted with the velocity, and this is a time integral where we have the force of on point P dotted with the velocity, and this is from time 1 to time 2. Now this definition is for a single particle with a single force of F sub P. Now if we add forces to this, then we can continue this, and by taking all the forces, we can say that the total work that's done on the particle, this is due to all the forces that are acting on the particle, same thing defined by the position vector that's moving along this path, is equal to the change in kinetic energy of that particular particle. So from time 2 minus time 1, or from time 1 to time 2. And this we call the work kinetic energy relationship for a single particle. Now to extend this to a multi-particle system, we drop our subscript P and we replace that with an I. So just saying that we have multiple particles, let's say we have n number of particles, and for each particle I, we have the same relationship in which the total work, which is due to all the forces that are acting on that particle, are equal to the change in kinetic energy across time 1 to time 2 on that particle. And with each particle that's in a system of multiple particles, the forces we define as either an external force that's acting on the particle or internal forces that are acting between the particles. So the external force with a superscript ext, and then the internal forces have the subscript I, j or j, I. So as a result, the total work on the system is going to be equal to the work due to external forces plus the work due to internal forces, in which we keep the same notation, and we're using the path integral for the force and all the external forces dotted with the differential position vector, and then for the internal forces, it's the force I, j of internal forces, and dotted with the same position, or the position vector of the relative position vector between the particles. Now in multiple particle systems, we can get the total work by summing from I is equal to 1 to n across all the particles. And so this gives us that the total work for the entire system is equal to the total kinetic energy at time 2 minus the total kinetic energy at time 1. And when we sum across both of these terms, we get two terms for the total work. So we have the work, which is the total work due to external forces, plus the work due to all the internal forces, and then this is equal to the total kinetic energy at time 2 minus the total kinetic energy at time 1. And we've define this as delta T sub O, which is the change in the total kinetic energy. So now let's take this relationship that we've established for any multi-particle system, and then let's extend that to rigid bodies. So recall our definition of a rigid body. We said that a rigid body consists of at least 3 particles that are non-collinear, and the distance between all the particles doesn't change. And so another way to write that is that R, I, j, the norm of this is equal to a constant. And so when we apply these conditions to our definition for our work and total energy, is that when we look at the internal work, we see that regardless of the path and regardless of the force, the differential position between the two particles that are in a rigid body is always going to be 0. So our internal work in a rigid body will always be 0. And this means that the only work that's done on a rigid body is done by external forces, so we reduce our notation and we just call this W. So recognizing that the work is always done by external forces, and this is equal to the change in the total kinetic energy. And we've already established that the kinetic energy can be separated into translational, which we have as the T of G sub G with respect to O, and then rotational, so it'd be the change in the kinetic energy about the center of mass. And so this is saying that we have the total work on a rigid body is equal to the change in the total kinetic energy of the center of mass relative to an inertially fixed point, plus the change in the total kinetic energy about the center of mass. This is a nice conceptual observation to make, and we have our kinetic energy into a working form that we've established before, but still our total work on the system is, we've defined this as the summation of all of our particles, and this is of our total work R, I with respect to O, along our path. And we still need to turn this into something useful. So let's rewrite this in the terms of our velocity form, in which we're integrating over the power, so it's 1 to n, and we're integrating from T1 to T2 of the external forces on each of our particles, dotted with the velocity of I with respect to O as observed in the inertial reference frame across our time. Let's rewrite the velocity of I with respect to the inertially fixed point as the vector triad that takes advantage of the velocity of the center of mass, then plus the relative velocity of each point or particle relative to the center of mass. We make this substitution, and now we have two terms, in which the first term has the velocity of the center of mass with respect to the inertially fixed point, and then the second is dotted with the velocity of the particle with respect to the center of mass. And so here we have the summation of all the forces, of the external forces, and this is simply F sub g. And note, to do that we could switch the integral with the summation here to make the sum of the forces. And this leaves us with the time integral from 1 to 2 of all the external forces, which we've already defined as F sub g, dotted with the velocity of the center of mass with respect to the inertially fixed point. And by definition, this is the work on the center of mass by the external forces, and we can write this as W G with respect to O, and using the work kinetic energy relationship, this is T of G with respect to O, so the kinetic energy of the center of mass with respect to an inertially fixed point at time 2 minus the kinetic energy of the center of mass with respect to an inertially fixed point at time 1. So this is our translational kinetic energy, or rather the change of our translational kinetic energy. And looking at these expressions, what this tells us is that if the total external forces on a rigid body is equal to 0, then the translational kinetic energy doesn't change, or the translational kinetic energy is conserved. So now let's take a look at the second term, in which we had all the external forces on the single particle dotted with the velocity, which is the relative velocity of the particle with respect to the center of mass. And so for a rigid body, we have this definition, which is the velocity of any point on the rigid body is equal to omega b as observed in the inertial reference frame crossed with the position vector of I with respect to that point, which is the center of mass. So we substitute this expression into the term that gives us our relative velocity, and then we apply a vector identity, and this identity allows us to take this form where we have A dot B cross C and rearrange that to C cross A dot B, And then that gives us a nice expression where we now have a position vector crossed with our force vector dotted with the angular velocity vector. Now notice also that I switched these two terms, which was our integral and our summation, which we can always switch when needed. And what we see here is that r cross f here is the moment about the center of mass due to all the external forces. And so all that was left when we separated our work was a work about the center of mass, and this is equal to the integral of our external moments dotted with the angular velocity as observed in the inertial reference frame from time 1 to time 2. And so this work is equal to the change in rotational kinetic energy. And similar to what we had before, we see that if there is no external moment working on the rigid body, then the rotational kinetic energy doesn't change. So the rotational kinetic energy is conserved when there's no moment. And so in summary, what we have are the work-energy relationships for a rigid body, which says that we have the total work on the system is going to be the work on the center of mass due to the external forces plus the work about the center of mass, or relative to the center of mass, which we've defined as W of G with respect to O. We can write this in two forms, either as the path integral of all the forces, external forces, dotted with the differential position vector, or we can take the time integral of all the external forces dotted with the velocity of the center of mass with respect to O. And then for our rotational work, or our work about the center of mass, it's the integral from time 1 to time 2, time integral, of the moments due to the external forces dotted with the angular velocity as observed in the inertial reference frame. And the relationship with energy is that this is the change in the total kinetic energy, and then we have our expressions where our work on the center of mass due to external forces is equal to the change in the translational kinetic energy, and then the work about the center of mass due to this moment is equal to the change in the rotational kinetic energy.